Hello, we're presenting our project poster at the ISC 2020, which is held in a purely digital form. Our project is called ExaNIML, an abbreviation for Exascale library for numerically inspired machine learning. It's a joint project between the Technical University of Munich, Germany, so me, Hasan, Ashraf, Tobias, Neckel and Hans Bungartz, and from the University of Texas at Austin, George Biros. As the title suggests, we're working on an interface between a high-performance computing and machine learning, like many here. But let me just reiterate why I think it's important. There's a general gap between communities. Since they are often different people, there are different focuses. As machine learning needs considerable computing power, we need adequate software. Machine learning needs to be computationally efficient and best with enough concurrency for next-generation distributed compute systems. The HPC can contribute significantly to the machine learning movement by, for example, performance engineering, which is greatly undervalued by the machine learning community. Next to optimizing performance, ExaNIML has two method blocks, namely GoFMM and sparse grids. For the Supercomputing Conference 2018, we have developed a matrix approximation scheme. Matrices can be often the memory and compute bottleneck in programs to their quadratic complexity. GoFMM is an approximate n log n method with asynchronous dynamic scheduling. The distributed memory setup sketched here on the slide, the white regions remain untouched. The other colors represent the four nodes holding this matrix. For the examples here, K is a kernel matrix, G is a graph Laplacian, and H is a Hessian matrix. Compare matrix vector multiplication times and for the approximate schemes also the compression time, and approximately GoFMM outperforms ScalaPack and StrumPack, which is a structural matrix package. Here, GoFMM is a matrix compression tool for very large matrices, and it relates to machine learning at numerous places. Just as an example, deep neural networks, one often uses gradient-based methods, or variants of them, and GoFMM can allow for second-order schemes like a Newton scheme, where we, with GoFMM, enable memory and compute boundaries. So, in summary, GoFMM creates a very coarse, lower-dimensional subspace based on importance sampling. Then on those coarse subspaces, we want to apply sparse grids in the future for more accurate representation.
For applications such as manifold learning, we are currently exploring the combination of kernel approaches with sparse grids. The kernel approach can be used to obtain a coarse approximation of the solution, which can then be refined through sparse grids. The main attractiveness of these sparse grids is that they provide rigorous error bounds for the approximation and are relatively resilient to the cursive dimensionality. Sparse grids are based on the representation of a function in a hierarchical piecewise polynomial basis, as you can see in the top image on the right. This can be extended to multiple dimensions through a tensor product formulation given certain smoothness guarantees on the function to be approximated, that is, bounded, mixed, second-order derivatives. Sparse grids can be computationally feasible as compared to full grids, even in relatively higher dimensions, since asymptotically the number of grid points required in d dimensions scales with log of n to the d, as opposed to n to the d for a full grid solution, without incurring a huge approximation error. The bottom figure on the right shows a typical sparse grid in 2 dimensions. One approach to obtaining fine sparse grid solutions is to combine coarse full grid solutions as shown in the image on the right. This is called the combination technique, and it has been used in highly scalable sparse grid solvers. In terms of software, we are currently working with SG++, which is a popular HPC library for sparse grids. The library provides sparse grid solutions for data mining, uncertainty quantification, and partial differential equations, among other things. Thank you for watching this video. We hope that our project has piqued your interest. If you're working on something similar, have any comments or criticism of our project, please do not hesitate to contact us.